So one of the things that comes up pretty much everywhere in machine learning for binary classification tasks is the receiver operating characteristic, which is usually shown as a curve. And if you've been doing machine learning for any amount of time, you know, right, that in general, when you look at curves like this, ROC curves, the general strategy is, okay, the further this curve is from the midline here, the better your binary classifier is. And in general, you can summarize that distance from the midline by just taking the area under your ROC curve. Okay, so that's the area under the curve, or the AUC statistic. The closer that statistic is to 1, right, the closer you are to maximizing the distance between your ROC curve and the midline, which is why that statistic works so well. But the thing that I've been thinking a lot about lately is like, okay, well, but what even is this plot, right? Like why is it useful? What are we plotting? Where does this curve come from? And I think probably a lot of people would be hard pressed to give like a concise and succinct description of what this plot shows you and why it matters for your model performance. So that's what we're going to go over today. We're going to do this inside of a notebook. Hopefully we can get this through in more or less one shot. So to start here, let's generate 100 examples. And what we're going to do is we're going to generate a set of random binary labels. All right, 0 or 1, and we'll set 100 of those. All right, so what we're doing here is we're creating an array of 100 random binary labels, either 0, which would be our negative class, or 1, which we will call our positive class. The next thing that we're going to do is we're going to generate a set of random predictions for those labels. And we'll do that by sampling from a uniform random distribution, 100 times. We'll do that as well. And if we stick everything inside of a data frame, let's call target the column containing our true labels, and prediction will be the column containing model predictions. If we take a look at this data frame, let's look at the top 10 samples. All right, you can see we have a randomly generated target, and then here we have our model predictions. Since this is a classification task, right, though, we want to have some way of converting our continuous model prediction into a predicted target class, right? The standard way of doing that is you just set some threshold. In this case, we'll set it arbitrarily at 0.5. This can be higher or lower, but we'll start at 0.5. And let's say that the predicted class of any given observation is if the prediction is greater than or equal to our threshold, we assign it the positive class of 1, else it's 0. And now if we take a look at our data frame, right, you'll see everywhere our prediction is above our 0.5 threshold, we've predicted the class as 1, else 0, right? And this is usually how this goes. So the question then is, okay, well, how good of a job does this classifier do? Does our random classifier do for predicting our random target? And in order to understand that in meaningful detail, I would say, what we need to do is we need to look at a confusion matrix. All right, so your confusion matrix, and for this, I'm just going to use the sklearn implementation. I'm not going to write this from scratch because that would just be a little extra. It's a simple function. We provide our target and then our predicted class. And we're going to get back basically an explanation of all the different ways our model is right and all the different ways that our model is wrong. So let me just write out here, we'll use Seaborn heat maps are a good way to visualize these confusion matrices. And then what we want to do is we just want to do some labeling. So we'll set the X label to be predicted class. We will set the Y label to be the actual class, right? So that's going to be our Y-axis. And then we'll just explicitly set the X tick labels because I think by default they get a little weird. y, and I think this gets us what we want, more or less. So let's see here. Yeah, okay, good. So this is our confusion matrix, right? And this is, your confusion matrix is a 2 by 2 because there's 2 ways for your model to be right and 2 ways for it to be wrong, right? The 2 ways for your model to be right is if it predicts the positive class when actually the observation belongs to the positive class, so that's your bottom right quadrant. And the second way it can be right is if it predicts the negative class when the observation is actually a member of the negative class. It's called a true negative, okay? So you have your true positives and your true negatives. The flip side of that is false positives. So that's where your model predicts that an observation belongs to your positive class when in fact it doesn't. And then you have false negatives. That's when your model predicts an observation belongs to the negative class and it doesn't, right? So 2 ways to be right, 2 ways to be wrong. Now for ROC, if we take a look back at our ROC curve here, you'll notice the x-axis is false positive rate and your y-axis is true positive rate. Now what your true positive rate is it's your number of it's your number of true positives divided by your total number of actual positives. So in this case, we have 20 divided by 20 plus 25 or 45, right? And that is your true positive rate. Your false positive rate is the same thing, but for the row above it. So it's your number of false positives divided by the total number of actual negatives, or 27 divided by 28 plus 27, which is 55. So what your true positive rate summarizes is how well does your model perform on instances of your positive class, right? If your true positive rate is high, you're predicting positive quite frequently, which means you're doing a good job at identifying your positives. Your false positive rate tells you how good the model performs on instances of your negative class. All right, so think about that for a second. If your model does really well at predicting your negative class, all the volume is going to be in the true negatives with very little in the false positives. But if your false positive rate is high, that means that almost all your volume is in false positives. Very little is in true negatives. So that's poor performance on the negative class. So that's the 2 quantities that we care about from the perspective of our receiver operator curve. So for our example here, let's say our true positive rate is going to be equal to, we said it was 20 divided by 25. And our false positive rate was equal to, what was it, 27 divided by 55, I believe. And if we make these F strings and print that, our true positive rate, sorry, this is 45. So our true positive rate is 0.4 repeating, and our false positive rate is 0.49. Now, this is just 1 point on our ROC curve. It's just 1 point along this curve. The way that you get all of the points along this curve is by using every possible threshold that you can use. In other words, calculate the true positive and false positive rate for every unique model score that you have. And then when you plot them against each other, you get back the ROC curve. Now, to actually do this here, what we could do is we could define a function to calculate true positive rate for a threshold, define one to calculate false positive rate for a threshold, and then run it in a for loop over every possible model score. Okay, you could do that, but this is Python, so that's going to be unbelievably slow. And if you try and do that over any more than about 100,000 observations, you're going to be waiting until Christmas for your code to finish. So there's a really cool vectorized dynamic programming trick here to calculate your ROC curve just blazing fast. I just about fell over when I saw this in the sklearn documentation. So here's how this works. Let's start by creating a new data frame. We'll call it df sorted, which is equal to, I'm only going to take the target and the prediction for our from our original data frame, and let's sort this by our predicted value, and we'll do this in descending order. All right, and then if we take a look, We'll take the first 20 and we'll take a look at it. All right, so here's our data frame sorted by predictions in descending order. Let's imagine that the first threshold that we use is this one. All right, just the largest prediction from our model. What's our true positive rate at that threshold? Well, how many true positives do we have? We have 0, right? Because the model is predicting this observation has a class of 1. Actually, it's a 0, so that's a false positive. We have no true positives. So the number of true positives is 0, divided by the total number of instances of the positive class is just the sum of our target column. All right? So in this case, your true positive rate is 0. If we use the second score as our threshold, now we have 2 observations we predict as belonging to the positive class, but we still have no true positives. So our true positive rate is 0 divided by the sum of the target column. Let's skip down here to this observation, right? If this is our threshold, we now have 1 true positive because we would predict everything above this as having a class of 1. And in this case, that's actually true. So here's our true positive. So our true positive rate is 1 divided by the sum of our target column. Just one more, I promise, and then the pattern will be pretty clear. If we just move the threshold down by 1, the number of true positives is the sum of our target column up to this point, right? Notice that's true for every possible threshold. If this is our threshold, the number of true positives we have is just the sum of our target column up to this point. Okay, down here, the number of true positives is the sum of the target column up to this point, right? The denominator is always the same. It's just the sum of your target column. So if we want to calculate true positive rate for every possible model threshold, what we do is this. Your true positive rate is equal to the cumulative sum of your target column divided by the sum of your target column. All right, or, you know, if you think about this in NumPy version, right, it's the cumulative sum of your target vector divided by the sum of your target vector. And if we calculate this out, and let's look at the top 20 again, here is our true positive rate for every possible observation. So what cumulative sum does is exactly what we just described. If this is our threshold here, the cumulative sum at this point is the sum of the target column up to here, right? Cumulative, that's what we mean. The cumulative sum at this element in your array is the sum of the target column up to that point, so on and so forth. So that's where that comes out. And that's your true positive rate. Now, if we were to do false positive rate of FPR, okay, it's very, very similar, except we do this. We switch the target column in this way, like this. All right, now why? We'll just talk it through, you know, really, really simply. So we know for false positive rate, this is the number of false positives divided by the total number of instances of our negative class. Well, for our denominator, right, for our denominator, how many instances of our negative class do we actually have? Well, it's the number of zeros in your target column. So if instead you switch your zeros to ones, that's what this bit of logic does. Now you can just sum that vector and you get the total number of instances of your negative class. How many false positives do we have for a given threshold? Let's pick here. All of our false positives is everywhere we got a 0 above here. This is a false positive, this is a false positive, this is a false positive. Because again, everything above this threshold we predict as belonging to the positive class. So everywhere there's a 0, that is by definition a false positive. So instead of counting up the zeros, just flip the zeros to ones, the ones to zeros, and take the cumulative sum again. And that will give you the total number of false positives up to any possible model threshold. So this little bit of logic will calculate your false positive rate for every possible model score. Now, the interesting thing to point out here is if you look, our true positive rate and false positive rate increases at roughly the same rate, okay? So they start off at 0. By the time we get down here to the 20th observation or so, we're at 0.15 and 0.23. So we're going to be very close to a linear trend here, which makes sense, right? Because we generated a bunch of random predictions. So if we plot our true positive rate, our false positive rate, so DF sorted, FPR against our true positive rate, and then let's also plot the midline, like so. And for this, we'll use a dashed red line, I think is like the best way to do this. And then we'll just label our axes really quick. So our X label is equal to false positive rate. And our Y label is equal to true positive rate. Plot this. Here is our ROC curve. All right, and you can see, again, we generated a bunch of predictions from random chance. So we're going to be really close to this trend line here, the midline, I should say. The last thing I want to talk about basically on this curve is why this midline here is like random chance. Okay, so if you think about a really good binary classifier, regardless of the threshold you choose for that model, your true positive rate you would expect to be relatively high, and your false positive rate you would expect to be relatively low. And so when that's the case, when that occurs, when your true positive rate is higher than your false positive rate, you end up above this trend line here, above the midline. And the better your binary classifier is, the closer you get to the top left corner. So the perfect binary classifier has a 100% true positive rate and a 0% false positive rate, okay? If you're below this curve, though, a really interesting thing is true. If you are below this curve and you have a really high false positive rate and a really low true positive rate, what that means is that your model is actually really, really good at predicting the opposite of the class label. So if you just invert the model predictions, again, now you have a good binary classifier. So really, anything top left, bottom right indicates that your model does a good job of predicting your target or the opposite of your target. So really the only thing that's left over is your midline here. If your false positive rate is roughly in line with your true positive rate, then you are evenly distributing your model predictions between things that are actually true and actually false, which means you're basically at random chance, right? So that's where that comes out from. I just wanted to make that really clear. So the last thing to talk about is just the area underneath of this curve. It turns out that it doesn't matter that much the dynamics of your ROC curve. So it doesn't matter that much that like here on the curve we're below the midline, up here we're above it slightly, and then here we're kind of on it. That doesn't tell you that much useful information about your binary classifier. So instead what we do is we just summarize this curve with the singular statistic of the area underneath of it. So notice the larger the area underneath of this curve is, the closer it gets to the top left corner here, the better the binary classifier is. So that's why we use that as a statistic. I think that's kind of obvious. Calculating this, though, is kind of cool. It's a cool exercise. Basically, what you do is you use Riemann integration. And if you think back to your calculus class, Riemann integration basically says to get the area underneath of a curve, what you're going to do is you're going to draw a bunch of rectangles underneath of it, and you're going to sum up their area. Kind of makes intuitive sense, right? So if we take a look at our data frame, right, our false positive rate, this is our x-axis, and our true positive rate, these are all the points of our y-axis. It's nice that our column here is sorted in ascending order because the width of our first rectangle we need to sum is given by the first false positive rate, is given by the second false positive rate minus the first. The width of the second rectangle is given by the third false positive rate minus the second. and so on and so forth. So if we can take the difference of our false positive rate column on itself, but offset by one element, we'll get all of the widths of these rectangles. So what that looks like is this. We say df sorted of our false positive rate, and what we would like to do is something simple like this, where we start at the first element, take everything after it, and then subtract from that the same vector except only up to the last element, all right? And this will give you that offset difference that we just talked about, okay? This is the vectorized way of doing that. However, the thing about this is, and this is something that I do not like about pandas, is the fact that these are series and they have indexes. So let me show you this. If we take a look at this, you see that there's indexes. That's what these values are here on that leftmost column. When you subtract this array from, or sorry, I should say this series from this series, it doesn't do the subtraction based on the relative position of elements. It does it based on the index. So it will subtract the element with index of 2 in this array from the element of index of 2 in this array, and the element of index of 3 from this array to the one in this array. What that means is that this will only ever give you a result of zeros because you're subtracting the same elements. I don't like this behavior from pandas. I'm sure somebody who maintains that library could yell at me and tell me why they do this. But the way to get around it is just to convert the series into NumPy arrays. And what you will get back is an array of all the widths of your rectangles. You can see here that what we have is constant width. That's kind of interesting. I'm sure there's a reason for that. But these are our widths. It's this. And then our heights is just going to be, right, we said the value of our true positive rate, except we're going to start at the first one and take everything after that so that we have the same length of an array. And we'll just convert this to a NumPy array as well. Now to take the widths, multiply it by the heights, and sum everything up, we can just take the dot product. So of the widths times the heights, this here will be our area. And we can print area under the curve is equal to this calculated area. And when we run this, we have our AUC of 0.443232, whatever. Let's compare this to sklearn. So sklearn has this ROC AUC score. And what we can do is df sorted. Our target is our ground truth. And then provide our prediction. And when we run this, you can see that we are getting up to a very high level of precision the same answer, right? 0.44323232 repeating. And this may be a floating point error. This may be because they stuck a 0 in front of your the floating point column so that there's continuity from the origin. It could be a couple things. Actually, that doesn't make any sense because the area of that rectangle would be 0 anyway. This is probably floating point error. At any point, we're close enough. So that is kind of the whole top to bottom of ROC curves, why they matter, how you calculate them quickly and efficiently, area under them and how you calculate it. I got kind of nerd sniped by this, but I had a really good time. I recommend, if you're interested, going through the sklearn implementation of this ROC curve function, because there's a lot of really cool stuff in here about writing really good quality, stable software for numerical computation. Like they do things like check for sharp points in the ROC curve using the second derivative to basically, remove any sharp jumps up and down. So you always get like a smooth curve. They dedupe, they basically get the unique model scores by looking at the first derivative. There's a lot of really cool stuff in here that I would just go through if you have the time or the interest. They also use NumPy in here. So NumPy implementations in general are going to be faster than pandas. I would do it that way for this, but I think it's easier to see everything all lined up in a data frame. So anyway, that's everything on ROC. I hope that was useful, and that's it. See ya.